Good afternoon.
Good afternoon, ma'am.
Good afternoon, ma'am.
So now I am starting my today's class. Okay. In the last class, yesterday we have discussed about the basic logic gates and their truth table. And there are two universal logic gates, NAND and NOR. Do you do you have any question from that section?
No, ma'am.
So now this is another logic gate which is known as XOR gate. XOR in short form, it is exclusive OR gate. Why it is exclusive? Because this gate can be used for many operations like addition operation, parity checking, for bit comparison. That's why. Okay. So as these gates has various functions, this gate is known as exclusive gate. And now see the operation of exclusive OR gate. From the truth table, I am giving you the operation tips to remember it. See, if the number of inputs is 2, so there are 4 combinations. How we can write the output from this input? For XOR gate, if the number of input or number of 1 is odd, number of 1 in the input section is odd, then the output will be 1. But if the number of inputs, that is 1, when both the inputs are 1 in case of 2 inputs XOR gate, so number of ones here 2, which is a even number. So if even number of ones are present in the input side, then the output will be 0. See the truth table and try to understand the point. Here, one input is 1. That is, how many ones are there? 1. This 1 is odd number. So if odd number of ones is present, then the output will be 1. But here, number of inputs 2, both are 1. So how many ones are there? 2. And this 2 is even number. So if even number of ones are there, then the output will be 0. Got this point?
Yes, ma'am.
Okay. Then from truth table, you can understand this. So what is the logic symbol for 2 input XOR gate? It is just like OR gate, but it is separated by a parenthesis like symbols. So this is the logic symbol of a XOR gate, 2 input XOR gate, and this is the output expression for XOR gate. If we write A plus B, it is OR gate. But when this plus sign is within a circle, then it means it is exclusive OR gate. And what is the output expression? A naught B plus A B naught. Take any one case from input. Suppose A is 0, B is 1. What will be the output? Why? If A is 0, B is 1. When A is 0, then A complement means it will be 1. Then 1 dot B is 1. 1 dot 1 means we will get 1 here. Then from this term, A is 0, B is 1. So complement of B give us 0. Then 1 dot 0. 1 dot 0 means actually 1 and 0. So it will be 0. So finally, here it is 1 plus, here it is 0. So 1 plus 0 give us 1. So when this conditions comes, the output will be 1. So this is the output expression. You should remember it for two input XOR gate. It is A naught B plus AB naught. Clear?
Yes, ma'am.
Here we write some functions of XOR gate. XOR gate acts as an inequality detector. This term is important here. Inequality detector. Inequality means inequality in the input side. Here, both the inputs are 0. It means both the inputs are in same condition. Their output is 0. Here, both the inputs are 1 and we may call both the inputs are equal. Then the output is 0. But when the output is 1, when the inputs are not equal to each other, one is 0, another is 1. Here, this one is 1, another is 0. So, when the inputs are not equal, then the output will be 1. That's why it is used as an inequality detector. We can detect the output when the inputs are not equal. Clear?
Yes, ma'am.
So now I am going to the next section, next topic, that is Boolean algebra and De Morgan's theorem. You know the basic algebra, okay? With the help of algebra, you can solve various problems. But here, why it is called Boolean? Because George Boole developed these rules. That's why it is known as Boolean algebra. And using this algebra, we can solve various Boolean functions. So what is Boolean? Actually, in case of logic gates, the inputs are known as Boolean variable. You can use capital alphabets in capital letters or in small letters, but you should take alphabets only, okay, as input as well as output. For example, A, B, capital A, B, X, Y. These are all variables can have only one of the two possible values or at any time. What are these two possible values? In case of digital systems, you know, it follows the binary number system. So any variable, it can take only the two distinct values, that is 0 or 1. And such variables or such symbols are known as Boolean variables. Now, next, some basic laws of Boolean algebra. We should remember this and we can understand this also. Suppose this section is somehow related with this. How? See, here all are in OR operation. Here all are in AND operation. There are basically three operations, you know, AND, OR, and NOT. You know the function of not, because if we put 0 at the input side, we will get 1 at the output side. That is, the not function means we will get the complement output of the input. Here, these are OR laws, OR. These are valid for OR operations, and this side, that is from 5 to 8, valid form for AND operations. Okay. So, if we OR any variable A, B, C, D, X, Y, Z, any variable with 0, what will be the result? A. Because output depends only on the A. Check, if A is 0, then 0 plus 0 give us 0. If A is 1, then 1 plus 0 give us 1. So actually output is equivalent or equal to A. In the case of AND law, any variable, whether it is 0 or 1, if multiplied with 0 or dot or AND operation with 0, obviously the output will be 0. Here, OR operation, A plus 1. So any variable, whether it is 0 or 1 state, if we OR this with 1, what will be the output? 1. Because in OR operation, if any input is 1, the output will be 1. Here, for dot operation or AND operation, if we take a variable, if we multiply it with 1, what will be the result? Depending on A, check. If it is 0, 0 dot 1 give us 0, 1 dot 1 give us 1. So basically it follows A. So A dot 1 means A. Similarly, here A plus A give us A dot A give us A plus A bar. What will be the result? A plus A bar. At any instant, if A is 0, so A bar will be 1. Right? 0 plus 1, then what will be the output?
1.
1. So, check, if it is 1, then it will give us 0. So, 1 plus 0 give us 1. So, this is a rule.
ম্যাম হ্যাঁ ম্যাম বলছি ম্যাম এ বারটা কি করে 1 হচ্ছে?
A bar means A complement. Right?
হ্যাঁ ম্যাম
If we put A 0, then what will be the complement of A?
1.
ও
1.
হ্যাঁ হ্যাঁ 1
1.
হুম
Right? We will get it actually using not get. Just see the expression, okay? A plus A naught.
Okay,
If we put A is 0, then the complement output will be 1. Actually this expression becomes 0 plus 1. Right?
হ্যাঁ ম্যাম
So 0 plus 1 means 1. If it is 1, it will give us 0. Same thing, 1 plus 0 give us 1. For dot rule, A dot A naught, A dot A bar. কি হবে? 0. এটা আজকে ফার্স্ট ডে, জাস্ট প্র্যাকটিস, ডু ইট। A dot A dot A bar 0, A dot 0 0, A dot 1 A dot A bar. Check, if it is 0, it will be 1. তাহলে যখন ডট করবে, if one input is 0, another is 1, output will be 0. So A dot A bar is 0. These 4 laws for OR and this 4 for AND. And see, one important thing here, now just see one thing. These 4 laws maintain some properties. Check. If you put, just replace 0 with 1, then you will get this 2. Okay, if we replace 0 with 1, in OR operation it is 0. If we replace it with 1, we will get the same result. Here, if we replace this 1 with 0, what will be the result? A dot 0 give us 0. Here A plus A is A, same. A plus A bar 1, here only 0. So, this property is known as dual property of the Boolean algebra. Just replace 1 with 0 and 0 with 1, you will get the result. When both are A, you will get A in both sides. OR operation or AND operation, you will get A. Okay. Now, Boolean algebra supports some basic laws of ordinary algebra. Already you should know these 3 laws. One is known as commutative law, associative law, another is associative law, and third one is distributive law. This is very simple things it is. You can verify this expression with the help of truth table. You will get that taking left hand side, if you take this, you will get a output truth table. And if you take this in this form, b plus a, you will get the truth table for that. And after getting this 2 truth tables, it will show both truth tables shows the same results. It means a plus b equals to b plus a. Obviously, a dot b equals to b dot a. In associative law, if we remove this parenthesis, so a plus b, you can put here within this parenthesis plus c. You will get the same result in both sides. In dot operation, a dot b dot c, you will get the same result here. In distributive law, simple algebra, following the simple algebra, you should multiply both a, b, you will get a dot b. Then a will be multiplied with c, you will get a dot c. So both are same. Here also a plus b, c plus d, you will get 4 terms here, ac plus ad plus bc plus bd. And if you have this term ab plus ac, you can take a as a common term and you can write b plus c. Just same line written here, but it is in the right hand side, it is in the left hand side. So these 3 laws we will use for simplifying the Boolean equations. Now here some Boolean equations are given for simplification. Now what is y within bracket ABC? Each system has an output. Each digital system has an output. Consider this is the output terminal Y. And from here, you can guess how many input terminals are there in the system. In the system or in the circuit, there are 3 input variables. So, Y, that is output, is a function of A, B, C. And the output equals to ABC plus A bar B plus AB C bar. So you can implement this circuit by showing this equation with the help of basic logic gates. Suppose ABC, to generate this term, this is a AND term, right? A dot B dot C, ABC. you should take only one 3 input AND gate. Here, to get A naught B, first you should convert A to A naught. Then one NOT gate is required. Then A naught, that is the output, it will be multiplied with B, that is another AND gate is required, which is 2 input AND gate, A naught B. Then you will get this term. And here A dot B dot C naught. So to get the C naught, first connect one inverter with the C input terminal, and from the output you will get C naught. Then connect C naught, A and B, these 3 terminals with a 3 input AND gate. Then the output, it will be A, B, C naught. So now, how you can generate the OR between these 3 terms? Because one AND term, second AND term, and third AND term, they are with OR operations with each other. So you need another 3 input OR gate to get the final output Y, because here it is a one term, one AND term, another AND term, another AND term. So you should connect these 3 input to the inputs of the 3 input OR gate, and finally from the output you will get this Y. And then you can say that yes, Y is equal to ABC plus A bar B plus AB C bar. But to implement this, you can guess how many logic gates are required. Here one 3 input AND gate, here 2 input AND gate, here 3 input AND gate. And to get this complement, you should take 2 inverter gate. And finally, to get the OR between these 3 AND term, another 3 input OR gate is required. So 3 plus 4 plus 5, 2 NOT gate, that is 6 gates are required. So our purpose is to reduce the number of gates to implement the circuit that performs the same operation. So now how we can simplify the output expression here for minimization. So to simplify this equation, we will take the help of Boolean laws. Now, see, first one, ABC plus A bar B plus AB C bar. Okay, ABC plus A bar B plus AB C bar. This term will be actually B, not B naught, B bar. A bar B. So how we can solve, how we can minimize this? First consider this 2 term, ABC and ABC bar. Then take AB as a common term. Then C plus C bar, you will get C plus C bar here plus A bar B, right? A bar B. So from C plus C bar, what is the rule behind this? C plus C bar. C plus C bar give us
1.
1. So it will give us actually AB dot 1 plus A naught B. And then from these 2 terms, you can again take a common term, that is B. Then what will be the output? B, within bracket you will get A plus A naught. So here actually A plus A bar again 1. So ultimately it will be equivalent to B. So only using this terminal B, we will get the output, because the final output depends only on the B. It follows B. Here A C bar plus AB C bar, if we take AC bar. How you can solve this? Here 1 plus b, and 1 plus b means any variable when OR with 1, obviously the output will be 1 because it is an OR operation. So ultimately from here you will get AC bar. So there were two terms, but after simplifying you will get only a single term, AC bar. So in this way we can reduce the number of gates to design the circuit. This is not the best way. There are various ways to reduce the Boolean expression. But this way, if we solve the equation by using the Boolean laws, Boolean rules, and De Morgan's theorem. There are two theorems known as De Morgan's theorem. We can reduce the Boolean expressions, but it is time taking. So there are another methods to solve or to minimize the Boolean expressions. Boolean expression minimizations is required to minimize the number of logic gates. Okay. Clear?
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. Now, see
Yes, ma'am.
De Morgan's theorem. What is De Morgan's theorem? How you can memorize this theorem? First theorem, see the expression first. AB naught equivalent to A naught plus B naught. AB naught. What is this? This is NAND. Right? Two input NAND gate. AB naught. If AB is input, then AB naught means NAND. Right? Left hand side.
Yes, ma'am.
So, how you can memorize it? NAND is equivalent to bubbled OR. Bubbled OR. Bubbled means complement. So, if AB naught is there, first theorem states that it will be equivalent to bubbled OR. So, bubbled OR means if there are two variables, we will get the OR of the complement of each variable. A, B, there are two variables. So, it will be the OR of A naught and B naught. So, now the first theorem states that the complement of a product, here it is a product term, AB is a product term, that is AND term, complement of a product term. Now taking this, which is called complement of a product is equal to sum of the complements. Sum means this, or sum of the complements. Complements means there are two variables, so take the complement of each variable A naught and B naught. Sum of the complements, that is, if the variables are A and B, then we can write AB complement is equivalent to A complement plus B complement. And you can read it as NAND is equivalent to bubbled OR. Clear the first theorem?
Yes, ma'am.
Next, so NAND, you can remember NAND. Why it is NAND? NAND is a universal gate. So another one, it will be NOR. So second theorem states that the complement of a sum, sum means OR operation. So complement of OR means NOR. So it is NOR. So NOR is equivalent to bubbled AND. So we can read it in this way, nor is equivalent to bubbled and. If it is an or, then we take complement of this. That is, the second theorem states that the complement of a sum is equal to the product of the complements, complements of the variables, product of the complements. In equation form, this can be written as a plus b, then take complement. Complement means it is an OR operation. Then it will be equal to a naught dot b naught. So just say NAND is equivalent to bubbled or, and NOR is equivalent to bubbled and. When it is NAND, it will be OR. When it is NOR, it will be AND. Just a reverse. For AND, it will be OR. For OR, it will be AND. Clear?
Yes, ma'am.
Yes, ma'am.
So actually, De Morgan's theorem states the output of two universal logic gates, that is NAND and NOR operations. NAND is equivalent to bubbled OR and NOR is equivalent to bubbled AND. This is the De Morgan's theorem. So De Morgan's theorem, two theorems that are an important part of this Boolean algebra were proposed by De Morgan, and the first theorem is based on this NAND operations and second theorem is based on the NOR operations. So now based on this De Morgan's theorem, you can again simplify the Boolean expression. One expression is given here. Just try to solve it and you will get C naught. Just do it. Here De Morgan's theorem is not used. Here just simple laws are used. There are four terms: A bar, C bar, then A bar, C bar is here, then B plus B bar give us 1. From here, you can take A, C bar as a common part, B bar plus B give us 1. So finally from here, take C bar, you will get A plus A bar within bracket and it will give us 1. So finally it will be C naught. So when y equals to the OR of these four terms, which is equivalent to C naught basically. Then from here, here associative law and the rules are used. Here taking product of AB plus A bar B C D. Then rearrange the terms. C bar give us 1. Then from here D bar plus D give us 1. And finally from these two terms, by taking this B as a common, then A plus A bar will be 1. Then finally you will get B. Clear?
Yes, ma'am.
Okay. Now see, here De Morgan's theorem are used for implementation of basic gates with the help of universal gates. You know the definitions of universal gates. You have told yesterday that NAND and NOR, these are known as universal gates because we can implement the basic logic gates with the help of NAND gate only or NOR gates only. So here is the implementation part. To implement NOT gate from NAND gate, then AND gate from NAND gate, and OR gate from NAND gate. Here, two input NAND gate. If we connect both the input, connect means if we short these two terminals and take one input from these common terminals. So it will become a one input gate. What will be the output? If both the input now becomes A and A, so what will be the output expression? A dot A, then complement. So A dot A give us A. There is a rule, A dot A equals to A. A plus A equals to A. So now A dot A equals to A. So finally you will get A naught. So now in this configuration, this two input NAND gate is acting as a inverter. Clear?
Yes, ma'am.
Or Kushmit,
Yes, ma'am.
is it clear?
Yes, ma'am.
Then how we can implement the AND operation from the NAND? It is very easy because it is a NAND gate, right? So if we take the complement of this, then we will get the original output. If we take the double complement of any variable, suppose if we write A double naught, then we will get A again. Check. If you put A equals to 0, A naught, কি হবে? A naught will be 1. And then again the complement of that A naught, it will give us 0. So we will get the original input, right? So if we take the double complement of this product term, we will get the original term. Do you agree this?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So in this configuration, basically this is a two input NAND gate. You will get here the NAND operation, NAND output. Then using this configuration, that is to invert this term again, you should connect this two terminal of another two input NAND gate and feed this output with this input, and finally you will get the output Y, which is the complement of this, right? AB bar already chilo, then it will give us AB double naught, double bar. So finally we will get AB. So this portion give us the equivalent operation of AND. So in this way we can implement the AND gate using a two NAND gate. Two NAND gate. Here you will get the OR operation. How many AND gates are required to implement this? 1, 2 and 3. So 3 two input NAND gates are required to implement a two input OR gate. Is it clear from the diagram? See, A naught, B naught. Then take the NAND of that. NAND of that. So one input is A naught, another is B naught. What will be the output here? This is NAND. So one variable is A naught, another variable is B naught. So they are NAND. They are in NAND operation. So A naught dot B naught give us AND and then complement. So
Yes,
now
ma'am.
use De Morgan's theorem. This De Morgan's theorem states that NAND is equivalent to bubbled OR. NAND is equivalent to bubbled OR. Is it clear?
Yes, ma'am.
Yes, ma'am.
Then, if it is A naught, then bubble
Yes,
means
ma'am.
A double naught. Say, then A double naught give us A, B double naught give us B. So, we are getting A plus B, that is OR operation. So, in this way, we can implement, yes,
Ma'am, the word bubbled exactly where you are using, I mean, pointing to.
A
The word bubbled, where exactly it
bubble.
is pointing
Bubble
to?
means actually complement. This symbol is termed as bubbled. Okay. Suppose we will take the complement of AND operations. Then it is called bubbled AND operations. So bubble AND means actually NAND. Okay. Bubbled means actually complement.
Okay, ma'am.
Okay. Because in inverter gate, you have seen one arrow sign in logic symbol and one small circle is there. This circle is known as bubbled, right?
Okay, so putting that bar is only
Bubble
bubble.
means complement. We are getting the complement, okay? If we separate this bubble from here, this circuit acts as an AND gate. মানে আমি বলছি from this symbol, if we separate this or if we remove this small circle from here, this gates acts as an AND gate, right?
Yes, ma'am.
If we add this bubble, it indicates it is a complement of the AND operations. That is, this is the logic symbol of NAND. Clear?
Yes, ma'am.
So in this way, with the help of two input NAND gates, we can implement the OR gate. So using NAND gate, we can implement NOT gate, we can implement AND gate, we can implement OR gate. That's why NAND is known as universal gate. In this way, I will share these notes with you so you can understand here how with the help of NOR gate you can implement NOT gate, OR gate and AND gate. Okay. So using NAND and NOR you can implement the basic gates. That's why these two are known as the universal logic gates. And also another gate which is known as XOR gate. XOR gate also we can implement with the help of NAND gate. This is not the implementation of XOR gate using NAND gate. Here it is the implementation of XOR gate using basic logic gates, that is AND or NOT. If we break these expressions in this way, you can design the XOR gate. That is, with the help of AND gate, OR gate, NOT gate, we will design the XOR gate in physically. So Y will be A not B. A not B, see, one input comes here, that is B. This input comes via a inverter gate, so it is A naught. So here you will get A naught B. Another term is AB naught. So to generate this AB naught, take this one input from A directly, another input via this NOT gate or inverter gate, you will get the complement of B, that is B naught. So using this AND gate, you are getting A B naught. So finally, using this two input OR gate, What will be the output? Output will be A naught B plus A B naught. So it will give us A XOR B. So this is the implementation of XOR gate using AND or NOT gate. Up to this, is it clear?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Now here another implementation, XOR
Yes,
gate
ma'am.
using minimum number of NAND gates. Here we are taking the help of De Morgan's theorem. This is the implementations procedure of the XOR gate using NAND gates. And this is the way of implementations. In this way, we can implement or design the XOR gate using minimum number of NAND gates. In this way, only 4 2-input NAND gates are required. Another approach is there where 5 2-input NAND gates are required. So you should practice this one, how we can get the 2-input XOR gate using the minimum number of NAND gates. Minimum number of means this number of 2-input gates, NAND gates. How many NAND gates are required? 4. One to get this term A, B, naught. Another to get this term, this 2 term, 2 input NAND gates are required. And finally, from this 2 term, you will get the output using this NAND term. Here is the simplification. Here, AB naught, taking this input here, A, what will be the output? You will get the term here. This is NAND between A and AB naught. So A dot AB naught, which is in AND, then take complement. Here, B and one input comes from here. So B dot AB naught. Y is basically taking from this 2-input NAND gate. One input give us this term, another input is this. So what will be the output Y? Y will be the NAND between these two, NAND. So take AND, then complement of this. And using the De Morgan's theorem, that is NAND is equivalent to bubbled OR. You will get these two separate terms. And from here, see, it is double complement. So double complement means you will get the original term. Here it is the original term. Consider it is x. So x double bar means you will get x here. So this is x. Here consider it is y. So y double complement means you will get y here. Clear?
Yes, ma'am.
So in this way, if you try, then you can reduce. See, here again NAND operation. So use De Morgan's theorem. Then NAND is equivalent to bubbled OR. Here also NAND is equivalent to bubbled OR. Then you will get A naught plus AB naught. Here A naught B plus BB naught. And using the Boolean rules, A naught give us 0. Here B naught give us 0. So finally we will get A B naught plus A naught B. This is the output expression for XOR gate. So in this way, this is the implementation technique of XOR gate using minimum number of NAND gates.
Ma'am, this one is little bit big than the previous and an OR gate.
Yes.
Then why are we using this
Okay.
one?
Because XOR gates can perform various functions. For designing addition, adder circuit, for designing subtractor circuit, for designing inequality detector or equality detector, okay, or as a buffer, as an inverter, you can use only a two input AND gate, a two input XOR gate. Okay.
Okay.
That's why XOR gate is important. And if it is true that NAND is universal gate, so we should prove that we can implement any kind of gate with the help of NAND gate. That's why it is here. Okay.
Ma'am, it means with NOR it is also possible.
Yes.
Oh,
So in your book, it is available how we can implement the XOR gate with the help of NOR gate. Okay.
yes, sir.
Okay. Try that one also. So already time is over. Just see why XOR gate is known as exclusive OR gate. Okay. It can perform as a adder. Adder means you can add the binary bits with the help of XOR gate. We will explain it when we will design the half adder circuit or full adder circuit. So one operation says it can add the binary bits. Another is it can act as a inverter as well as it can act as a buffer. So try this one. How? XOR gate from the truth table. If you see one input, control input, if we put control input at 0, what will be the output here? Suppose it is a 2 input XOR gate and we are calling this input as a control input and put it at 0 voltage level. So what will be the output here? If we put this terminal at ground permanently, so one input is always 0, what will be the output here? It is written here, but you should understand this point. When control input is low, Y follows A. Agree?
Yes, ma'am.
How? If it is 0, suppose you put 0. What will be the output? When both are 0 or both are 1, output will be 0 in
0.
XOR gate. Okay, so it will be 0. If it is 1,
Both
what is
both
the...
are 1.
No,
Both are one.
this one is permanently ground. This is the condition. Okay, when we put
Then
this
output will be
control
one.
input
Then
at
1. Then output
low,
will be 1.
when control input is low, then output will be A. If we put A equals to 1, then output will be 1. তাহলে Y follows A. Okay.
Yes, ma'am.
Yes, ma'am.
Yes,
Yes.
ma'am.
In this reason, তুমি কি বলতে পারো, in this condition Y follows A and this operation is known as buffer. This term is known to you. I don't know whether you know this term buffer. Buffer means actually the output follows the input, or you may call it is the input follower. So output follows input. But see, if we put this at high level, what will be the output? If control input is high always, if we put this high,
0.
0 means
Complement of
if we
A.
put this at high means আমি বললাম plus 5 ভোল্টে আমি রেখেছি, if it is always give us one input, logic 1, ঠিক আছে, then what will be the output? If we put 0 here, then it will get 0 1 combination. What will be the output? 1.
Yes, ma'am.
Yes, ma'am.
If we put 1 here, what will be the output? both are 1?
0.
0. So y actually equal to a complement. So in this way, 2 input XOR gate can be used as a buffer, as a inverter. Clear?
Yes, ma'am.
So several applications are there. That's why it is exclusive OR gate. So it can add the binary bits, it can subtract the binary bits, it can compare the binary bits, it can get the complement output, it can generate the same output. That's why this is very, very important, which is known as XOR gate. So now up to this. Next, tomorrow we have the class at 1:45, right? Right?
Yes, ma'am.
Okay. Now taking the attendance. Obhibadun,
Present, ma'am.
Astik, roll number 62, Astik. Anubhav,
Yes, ma'am. Present, ma'am.
Shubhodip,
Present, ma'am.
Shunayana,
Present, ma'am.
Orunavo, 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 Shohom.
Ma'am, Orunava went to college
Present, ma'am.
to submit his documents today.
Oh, okay, okay. Shohom,
Present, ma'am.
Shopna,
67 present, ma'am.
Shopna, Orbov,
Yes, ma'am.
Arno, Arno, Shayok,
Yes, ma'am.
Binayok,
ম্যাম অর্ণবের মাইক কাজ করছে না।
Arno.
Yes,
হ্যাঁ
ma'am.
ইয়েস ম্যাম অর্ণবের মাইক কাজ
Okay,
করছে।
okay, okay. Shayok. Shayok is there, right? Binayok,
Yes, ma'am. Yes, ma'am.
Seya,
Yes.
Present, ma'am.
Otanu,
Present, ma'am.
Shabik, Mohammad Shabik, সৌমাল্য,
Present, ma'am.
কে বললে?
Ma'am,
সৌমাল্য আর
Sabik is
মোহাম্মদ
present.
সাবিক। ওকে,
Ma'am,
সৌমাল্য
Yes.
ম্যাম প্রেজেন্ট।
প্রেজেন্ট, মিলন, শুভ্রজিৎ,
Yes, ma'am. Present.
সৌরাজ,
প্রেজেন্ট ম্যাম।
উপায়ন,
Present, ma'am.
অর্কস্মিত,
Present, ma'am.
সাত্তকী,
Present, ma'am.
দিস্তা।
Present, miss.
Okay, thank you. So Milon is absent, right? Milon?
Yes, ma'am. He is absent.
Okay. Okay, thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.